In this video we will talk about the gradient descent algorithm, and this would be the generic one, that is for an n a matrix having an n features. So last time we discussed in detail about the gradient descent algorithm, how it works, what is the math behind it, how to code that. But if you notice that our data set was house versus price, so we had only one features, area, which is the area of a house, and the price corresponding to that area is our y. So the x value, that is the features value, we had only one. But what of but in general we will see n m cross n database. So we will see what would happen basically if the number of features are more than one. So I would request you to please watch the previous video and then continue with this one. So by the end of this video you will have a clear idea of the difference between the abilities of linear and gradient descent, and also understand the generic gradient descent along with the associated mathematics. So this was the portion of the slide which I missed in the last video. So these are the types of gradient descent basically: batch gradient descent, stochastic, and mini batch. So what is batch gradient descent? It is the type of algorithm which is performed all at once. So suppose we were running a for loop. You saw that we were running a for loop in the initial function, and then in the inside the for loop we were every time calling another function, and inside that function we were again running a for loop. So we were basically having an O(n) square complexity. Uh, but what we were doing, uh, every time we get a new value of slope as well as the intercept, we just add to it, and at the end of that function it directly returns the value of the new cost function, right? So that was actually the batch gradient descent, because all at once it is done. So it is also known as vanilla gradient descent. It calculates the error for each example within the training dataset, but only after all the training samples have been evaluated does the model get updated. So after all the training samples you evaluate, you get the model updated. That is, after the entire while loop is over, then only you get to know what is the update. But for each step of the while loop, if you keep updating not only the m and c values but also the new m and c values, that is using the our gradient descent formula, so that is basically our stochastic gradient descent. So if you cannot understand, so I would just go back to our previous video. So this was our step gradient. So this is the general batch gradient descent. At the end of the while loop we are just applying the formula of new m, right? But what if at each iterations of the while loop we would have updated this new m? We could have done that also. Then that will be the stochastic gradient descent. Also we can do by some method, by some applying some breaks in an if else clause inside this for loop. By that we can also attain that after maybe 5 to 10 data points we uh, increment our value of new m. So that will be our mini batch gradient descent. So not a complete batch, but it will be in small batches. The data will be processed in small number of batches. So that would be our mini batch gradient descent. So do you think that gradient descent regressor, if we build something like that from our sklearn, would that be always better than linear regression? Now, in the very initial machine learning videos, I had told you that when you get a very high accuracy in a data set, you must get suspicious about what is actually the case. Is the data set being overfitted or something like that? You need to verify it very carefully. So gradient descent was expected to be a better model for minimizing cost function. Of course, it is an optimization function, isn't it? But will it always give better result? What if we try gradient descent on an approximately linear data? So let us just see what happens. So this is the same data set, price versus house, a house area versus price. So these are the x and y, and we did do the model selection and is for linear regression as well as for gradient boosting the regressor. So when we fit in the two objects 1 and object 2, we see that our linear regression model is giving 77.72 accuracy, but our gradient descent as expected gave a very high accuracy. But if you notice, this is on our training data. We are just on our training process. We haven't reached the unknown data yet. But when it sees the unknown data, our linear regression does not fall too much. It still gives 75% accuracy, but the accuracy of our gradient descent falls abruptly, 47.77% accuracy. So why this actually happens, if you think? So it happens basically because of the overfitting of data. The model has basically understood what is happening with me and how should I maximize it, but it is not generally leading to a proper function. It is not generalizing the function. It is specifically holding this training values only. It is not creating a general function of fx, but this has created a very general function. The linear regression, if you see, 77% and 75% are quite close to each other. So it on training and testing it performs similarly because a well-defined linear function has been generated for the linear regression, but here no such functions is generated. Rather, the computer has understood what is in the training data. So yeah, that's all from this. Now about this generic gradient descent, it is like quite similar what we did earlier. So this was our function. So let us just find out what to do for our data set as n features, as I told you, of n plus 1. So you know, for one features we can plot the straight line on a 2D curve. So it's quite simple. Y equals to mx plus c. How many parameters are there? M and c. We can also write it as uh, y equals to m1 x1 plus m2, right? We can also write this, or we can basically do m1 x1 plus m2 x2 equals plus m3 equals to 0, or we basically the two unknown values we can just put m and c. But if for one feature if we get two values, so of course for n features we will get n plus 1 values, because plus 1 because of one constant will be there at the end. So instead of yi minus mxi plus c, our generalized cost function will become something like this. When we put it into the formula of our mean squared error, our main cost function will look something like this. So actually m1 mn plus 1 xn plus 1 is actually the c constant value. We usually take it to be 1. Now means this xn plus 1 is basically 1, so mn plus 1 is a constant value and nothing else. So also our new equation we can obtain like this. In detail I have explained you in my previous video how this actually works. And so if we differentiate it, we for n plus 1 times we need to differentiate, right? For 2 times we differentiate for y equal to mx plus c, but here partial derivative we have to do n plus 1 times. For each m1 we have to do that. Then we will apply this formula. So what we did earlier and what we are doing now, here is a one-on-one comparison. So you can see earlier we had just m slope and c slope initialized to 0. We had points and learning rate. But if you see, this time we are creating a real life based data set, so it should be x train y train. We will actually train our model using this. So x train is basically an m cross of n plus 1 matrix. So earlier it was just m. Now you can easily understand that there are n plus 1 features, so there are n features, due to which it will be n plus 1. And ARR is an array basically containing the coefficients of and the length of ARR is basically n plus 1. ARR contains all the coefficient of our linear equation y equals to m1 x1 m2 x2, all the coefficient it contains. So earlier we just had an m slope, right? And it is just a single point which we are talking about, consisting of a single feature. But here we need to have an array of zeros. So for I traverse for n plus 1, I just append 0. So at every time we run the while loop, so just a second, every time we run the while loop, we will just update each of the values simultaneously. So just we need to add an extra outer loop n plus 1. You can see new m also I am appending as 0, and then it is just the same as the previous one, just an extra for loop on the outside function. You should try it working on your own computer. You can just pause the video, type down the code on your system, and just you can run it after some time. After watching the video, you can just run it and just to get a feeling of what's exactly happening. So list of the function is quite similar. We can just have an array of m as 0, and just for the number of iterations for each iteration we count what is the cost function, and this is the run function where we can manually set up the learning rate as well as the number of iterations, and this is the gradient descent function which we are calling from the run, and this is the predict values. So our testing data, if we take, we can predict the values this way, right? We can just traverse the while loop, and whatever answer we are getting, we can just append. So final m and in final testing data, whatever we get, we can just simply append it on our list, like, so that will be our y predict, because these are arrays after all, and final m and final testing data we will get from these functions. From the run function we will get the final m, and final testing data we already have, so we can just pass the arguments into the predict function, and we will get the y predict value also. So yeah, that's all from this video. From the next video we will be starting a new algorithm of machine learning. Till then, thanks a lot.